Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Fundamentals of Nano and Quantum Photonics. So this will be the last week of my discussion on nanophotonics. So the next 4 weeks will be on quantum photonics. So this week I would like to talk about atom cavity interactions, and then I'll also talk a little bit about nanofabrication. Okay. So the idea is that so far we have looked at the basic properties of the materials, and then we looked at different cavities, photonic, plasmonic cavities and dielectric cavities and so on, and what we can do with these cavities. So now in this week we will try to understand how a cavity interacts with incoming photons. So that's a very interesting frontier of nanophotonics, and we'll try to consider some of the basic concepts in this. Okay, the first one, we have already seen this in a different context, wherein we talked about the spontaneous emission, stimulated emission and absorption processes. We wrote the rate equations for that and the Einstein coefficients, right? So this I think we did last week. So I wanted to emphasize one particular aspect of it, which is the resonant. This is a resonant process. Okay, what do I mean by that? Let's say I have my two-level system like this. Okay, so even though I show this in an excited state, basically this is a two-level system. So E1, E2. Okay, if you have, like, let's say the valence band and the conduction band, then you have a band of states, and there are the corresponding optical signatures that you will see. But for a moment, let's consider this as a two-level system. Okay, if I have such a system, we talked about absorption process, which is captured by Einstein coefficient B12. And similarly, so the absorption process essentially takes a atom which is in the ground state, and it will put the atom in the excited state, and simultaneously the photon is extinguished. And the corresponding opposite process is basically spontaneous emission, wherein you have an atom in an excited state that will emit a photon, and immediately the atom will come down to a ground state. So if you think about it, what are these ground states and excited states? Right? These are not physically different. I mean, an atom can be in different states. So essentially these ground and excited states represent the way the wave functions are distributed in an atom. So think about it from the perspective of the particle in a box problem. We have this first state, second state and so on, wherein the wave function is different. So that we call as a different state. And the energy is different for those states, right? The only difference is physically it can just be a simple atom. But let's say if the electrons are confined in the center, the wave function, right, that is the lowest state, and then the highest states. If you have a spherical atom, the eigenfunctions will be slightly different, but you can still apply the same analogy of a particle in a box. So we have these basic states, right? Now, what do I mean by resonant process? So for that, let's say I'll consider a material like this, let it be a gas, and I subject it to a radiation with varying frequencies or energy. Okay. So now if I look at absorption, how will the absorption be in this scenario? So at a particular frequency where your h nu is equal to, let's say, h nu equal to E2 minus E1, right? At that frequency, you'll have maximum absorption. And if you are detuned from that, okay, that means if you are away from it, let's call this as omega naught. Okay, if you are detuned, let's say, that means I come with a frequency less than omega naught. Okay, slightly less than omega naught or slightly greater than omega naught. What happens? We see that the absorption very sharply falls. So in effect, what you're observing is, in a resonant process, the maximum absorption occurs at E2 minus E1 equal to h nu. And then absorption quickly reduces. As away from as you move away from the center, as h nu moves away from, let's say, omega naught. Okay. So this is a resonant process. Okay. And now one of the characteristic features of a resonant process is a line width. So if I look at this here, this I can calculate what is its FWHM. Okay. If I look at this line width, or I'll call it FWHM. Okay. It's extremely narrow if you're looking at a gas absorption in gases. Okay. Is small for gases. For example, if you're looking at emission or absorption from a sodium atoms, okay, the line width will be less than a nanometer. Okay, so less than 1 nm line width, even smaller actually. Okay, and FWHM is larger for solids. For example, if I look at, let's say, gallium arsenide, you'll never get a very sharp transition because you have bands and then there's a broadness of this, right? This can be even like 30 to 40 nanometers or so on. If you have quantum dots, I think it will be less than 20 nanometers, 25 nanometers or so. So these are very, very sharp. The line width depends on the type of system you're looking at. But in effect, you can think of any two-level system as a resonant system. Okay. Now, if you have such a scenario, Einstein description tells us what happens to the rates and all that. Okay. So what do we have? Let's say we have two states, E1 and E2. There are two levels, and the population of those states are N1 and N2. Okay. Now what happens? Okay. If you look at any particular Einstein description, you will see that, let's say, we start with some kind of a initial number of electrons in the initial number of atoms in the ground state. Okay. So there's one N10, and you shine light. Okay. You will see that absorption happens, and Einstein relation tells us that, or Einstein coefficients are there. So we can write N1 of t, the population of state 1, as a function of time. I can write it as N10 times exponential minus t by tau. Tau is my time constant, 1 over A21. Okay. So you'll see that the absorption, the population in the ground state reduces as a function of time, but it doesn't really tell us much about how the system evolves with time, in the sense, this tau is just the overall picture, phenomenological constant, but there's a lot more detail that we can observe. And for that, we'll have to look at the system a little bit closely. What we will do is, so we should recognize that these are essentially quantum mechanical states. So each level is a quantum mechanical state. Okay. And it has a wave function, right? Represented by a wave function. I'll call this wave function as n. The n state, right? First state, second state, and so on. So if you are having a two-level system, I can represent the overall wave function as psi equal to some c1 times first state plus c2 times second state. And I have two-level system. So this basically, this 1 and 2 are the Dirac's Kets Ket notation. So Dirac came up with this bracket notation. So in this case, these are Kets. Okay, for wave functions. Okay, and basically this C1 and C2 are the coefficients of it. So what this tells us is, let's think about it from the particle in a box perspective. You have this discretization of energy levels that happens when you confine an electron to a small dimension, and those states can be represented by orthonormal states, which are basically, they form a basis, right? So now you can form any other state which is a superposition of it. So 1 and wave function, in this case Ket1 and Ket2, represent two states. Now you can also have a linear superposition of which is represented in this fashion. So this should describe the complete quantum picture, right? So in this case, whenever you can write a wave function like this, so what is the probability of finding the electron in the state 1, right? So that will be the coefficient square. So if I look at it, in this case, C1 square and C2 square represent the probabilities of finding the system in a particular state, in a corresponding state, right? In the right. So now, so what? Okay. So what? So to answer that, let's consider a scenario wherein, let's take a purely classical case. In a classical system, if you have this, let's say the total number of atoms is n0, and from that there are n1 number of atoms in the first state or ground state, n2 in the excited state. Okay. So what is the probability of finding a atom in the n1 state or first state? So C1 square, in this case of a classical system, will simply be n1 by n0. Similarly, the probability of finding a system in the excited state is going to be n2 by n0. Okay. So if, because essentially what we are saying is, it is simply a statistical mixture. Okay. It just, if you take let's say 100 atoms, 40 atoms will be in state 1, 60 atoms will be in state 2, or vice versa. That's it. Okay. There is no interaction between the atoms. Okay. That's a classical situation wherein no interaction between atoms is considered. Okay. Now, so we'll in literature sometimes we call it a statistical mixture. Now, if you are looking at quantum picture and we are looking at the wave functions of each individual atoms, the wave function is also, basically we have seen how a wave function looks like. For a particle in a box situation, the wave function is, let's say, sine, right? And you have various periodicities of sine, right? You have seen those, wave functions, psi n pi x by a, right? So we can, n will dictate what sort of wave functions you're looking at. So I can write out even an exponential for it. Now suppose there exists, if like phi 1 and phi 2 are the phases associated with states, and there is a fixed phase relation between them. That means if I have phi 1 minus phi 2 equal to constant, okay, if I have this sort of a scenario. So essentially what we are saying is, there is a fixed phase relation between the wave functions of state 1 and state 2. Okay. So we call that as a coherent superposition. If you don't have this coherence, you end up with a statistical mixture where n1 by n0 and n2 by n0 will be the probability densities. But if you have a fixed phase relation between the states, then some interesting things will happen. Now, one of the analogies that we can think about in this direction is, even though we have not discussed interference phenomena in our course, but if you look at any basic optics course, you would have seen interference effects, wherein if I have two lasers coming in, they will, there are two different laser beams, they will not interfere because there is no fixed phase relation between them. So if I want to observe interference, what we do is we take an initial beam, and make it pass through, let's say, two slits. Now, because of from the same source you are deriving these secondary beams, they will interfere and then form these interference fringes. That means there is a fixed phase relation between the beams. So if you look at any particular position on the screen, depending on whether the waves constructively add or destructively add, you have these fringes that form. Okay, that's the classical optics picture, right? Interference. So now what we are saying is, if your wave functions also have some sort of fixed phase relation, what will happen? Okay, and to analyze that, it requires a lot more theory than what we need. So I'm not really going to describe any of it. Okay, so if you want to analyze such a system, we'll have to move to what is known as time dependent Schrodinger equation. Okay, so when we solve the particle in a box problem, that is a time independent Schrodinger equation. So we didn't take, we said simply H psi equal to E psi, right? So basically Hamiltonian applied on the wave function will give you the eigenvalue and the eigenfunction, that's it. But now if you want to actually solve this, so we'll have to take the time dependence into account, and this is my time dependent Schrodinger equation. I'll have to solve this. So I'm not going to solve it or anything. I'll just give you the final result with it. Okay. So remember we talked about the coefficients C1 and C2 for the wave functions, right? So now I can write an expression for the time dependence of the time variation of these coefficients. So what I'm doing here is I'm just listing out that the coefficient C1, okay, the time derivative of it is dc1 by dt, and that time dependence of C1 is going to depend on C2, okay, the coefficient 2, and I can also show that C2 is dependent on C1, okay. So they are cross coupled systems essentially, and it also makes sense. For example, what is the rate of change of population in, let's say, C1? Sorry? In classical situations? Sorry? That is the decay, right? Let's say, if you look at it classically, we said C1 is effectively, C1 square is going to be N1 by N0. So N1 is going to depend only on exponential minus E tau, right? It decreases. But the moment you are actually pumping it up, then the probability of atoms in the excited state is also going to influence finally. So there's going to be some equilibrium situation. So this is not one thing, if you have a simple two-level system and you keep pumping it, there's going to be absorption and the opposite process emission. And at some point they'll equilibrate. Eventually you'll end up with a situation which is, I think if you have two-level system, it should be N1 equal to N2 equal to N0 by 2. Equal number of atoms up and down if you have strong enough situation, right? Now in this case what we are saying is, we'll even go into finer details about it. Just one particular, in a way, we'll track what happens as a atom goes from the ground state to the excited state in time. Okay, so that is dependent on this. So wave function gives you at each instant of time. That's the classical picture is simply an average. Here it is basically you're tracking sort of each electron or each atom as it makes this transition. So now in this expression, one of the more important things is when you have things like this particular thing here is the transition frequency omega naught. I would say don't worry about too much the mathematics here, but the phenomena is interesting. So this is the input frequency, let's say. Immediately whenever you see this, right, this is a thing that we have seen multiple times in our linear differential equation. So you get a sinusoidal solution. So in effect, what we are saying is if you have a system like this and you pump it, you will see that the probability, this C1 square here, this is C1 square here. C1 square is going sinusoidally as a function of time. So down, up, and so on. This is a sinusoidal variation of probability of finding a system in the state 1. Similarly, there is a sinusoidal dependence of C2 as well. So as the function, so basically what's happening is if you turn on a beam, the system initially has highest probability of finding atoms in the ground state. Then with time, the probability of finding the atoms in the ground state reduces, and simultaneously the probability of finding an atom in the excited state increases. At some point, all the atoms are likely to be found in the excited state and then no atoms in the ground state, right? So if I have to look at this picture, I can say that in this case C2 is the dashed one, right? So let's look at this point. Okay, this is all atoms in ground state. Similarly here, at the same point, all atoms in excited state, right? And if I go in time, at a different time, I'll find the scenario reversed. So at this particular point of time, you will see all the atoms are in the excited state and no atoms in the ground state. So the probability of finding these atoms is changing as a function of time, and it is varying sinusoidally, and that particular frequency of oscillation of probabilities is called as Rabi frequency. Okay. So this particular frequency is called as Rabi frequency. And essentially what it tells you is this particular frequency is dependent on the dipole moment mu12. So here mu12 is basically the transition dipole moment. Okay. And E naught is basically amplitude of incident electric field. Okay. And so what we are noticing is, as you apply a pulse or a light pulse, the probabilities of finding the system in 1 and 2 states varies sinusoidally. Okay. And that particular frequency we said is Rabi frequency. So that is why here, if you look at it, in the bottom, you see here, this is basically, if I look at this, this is basically the period of oscillation, which is simply going to be 2 pi by omega r. If I do 2 pi by omega r, this is my period of oscillation. Okay. How much is this period of oscillation? Well, we can try to make an estimate. We said Rabi frequency is dipole moment times the electric field divided by h bar. So what is the dipole moment? If I take a atom, let's say, my dipole moment will be simply charge times A naught. A is the size of the atom, let's say, right? So I can say this is almost equal to 1.6 into 10 power minus 19 into atomic size will be, let's say, few angstroms. So I'll put it as 3 angstroms, 3 or 10 power minus 10, right? That's the unit of dipole moment. Okay, 10 power minus 19 into 10 power minus 10, so 10 power minus 29. And let's say my initial amplitude is E naught is 10 power 3 volt per meter. So what will be my Rabi frequency? My Rabi frequency will be simply omega r equal to 10 power minus 29 into 10 power 3 divided by h bar is roughly 10 power minus 34. So this is going to be about minus 29. I think is right. So 5 plus 3, 8. So 10 power 8 radians per second. Okay. That is my typical Rabi frequency in terms of radians per second, right? So what will be my period? My period of oscillation will be 2 pi by, let's say 10 power 8. Okay. That will be how much? 2 pi is 6.4. 10 power 8 is, I can take it up. So 10 power minus 8. So in this case, it will be 0.6 nanoseconds. Okay. The interesting thing is, what happens to this frequency as you change the amplitude of electric field? If I increase my amplitude of electric field, okay, my Rabi frequency is dependent on the electric field, right? If you increase that, Rabi frequency increases. So the period of oscillation reduces. Alright. When there are no coherent interactions, simply let's say the population is something, right? Let's say 100 atoms are in the excited state. Okay. Now the spontaneous rate, let's say the time is 2 nanoseconds. Then after roughly 2 nanoseconds, the population will fall down to 1 over E. That's it. So it will basically decay down to ground state. If let's say somehow you created at the initial time, you had 100 atoms in the excited state. After the radiative rate 1 over, if you take spontaneous emission, A21 coefficient, I think we have given a problem in week 7 also, wherein we said that A21 is let's say some 10 power 8 or something like that, and then 50 10 power 8 or something, and then 1 over that will give you the time. It will be 2 nanoseconds or something like that. So if you have 2 nanoseconds, after 2 nanoseconds, 1 over E population. So roughly, 67 or something. And then if you wait long enough, all the population will come back to ground state. There's nothing else. There is no oscillation that you can expect. If you don't have any coherent addition, then you don't expect oscillations. The question was, so is it a scenario where you are continuously exciting? The answer is no. You think of a scenario wherein, let's say, I can't, of course, if I say that without atoms, I can't excite them. Let me take it, in a situation, the initial state is that the excited state has population of 100. Okay. So if you're looking at a simple spontaneous emission process, I told you that after a time, 2 nanosecond, the population decays and nothing can be done about it. But what happens if your Rabi oscillations are fast enough? Then the population of higher state will be 100 and it will drop down to 0. And all the atoms will come down to 0, but then again they'll go back up and down and up. So basically you have this variation of population as a function of time. Okay. Now, your question I think will become clearer in this situation. Okay. So basically, the idea is, let's say you have this Rabi frequency, right? And the time period, let's say, is 2 pi by omega r is my time period of oscillations. And let's say somehow, I made this as 20 nanoseconds. Okay. And my lifetime of the state, let's say, is upper state is, let's say, tau r is about 2 nanoseconds. Now, will we see Rabi oscillations? We will not, because before even you can observe the Rabi oscillations, the excited state has decayed. Okay. So basically in this scenario, what's happening in this particular combination, right? Excited state population decays before Rabi oscillations can occur. Okay. Why do they decay? Why do the Rabi oscillations why cannot they complete? Because the decay is happening. What is the source of the decay? So so basically the reason for this is due to damping, I can say. And the source of this damping is twofold. One is your regular spontaneous emission, so population decay. Okay. So basically there is a lifetime associated with the upper state and they'll decay, that's it. So in some way they're leaking out. So you can think of this as some sort of oscillation occurring, but each time the oscillation occurs, some of it actually decays out. Right? It's emitting randomly into, spontaneous emission. So random process. Okay. Now you can also have another sort of damping mechanism, that is basically your dephasing, we call it. So basically if you have, let's say, if it's a system, there are some phonons, there's a collision, some collision happens, and the collision didn't really change the number of atoms in the excited state, but only change the phase of it. That will also cause some sort of damping. So in effect, we can think of what happens to Rabi oscillations as a function of a metric which is gamma by omega r. So basically I can define, let's say, this damping, if I call it as gamma, I can define basically gamma by omega r, which is a ratio of the damping to the Rabi frequency. If you have zero damping, okay, the first scenario that we just discussed last time, right? You have this perfect oscillation of populations will occur. Okay, so that is this particular first case. Damping is zero or negligible. Okay, or not zero. It's not negligible. Zero damping. This is basically no damping. Okay. Now let's say there is some amount of damping. Okay, moderate damping, wherein my damping coefficient is 0.1 times the omega r. If damping coefficient was 10 times omega r, what happens? Just quickly, just decays. Nothing will be seen. But in this case, damping coefficient, damping rate, not coefficient, damping rate, right? Damping rate is 0.1 times omega r. So if omega r, Rabi frequency was 1 gigahertz, let's say the damping rate was 100 megahertz. So I can see some oscillations. So second term you see here, is this initially there is an increase in population and reducing. This is oscillation of populations. So if I look at the probability, right, this is C2. So that means the excited state probability is going to vary initially as something, but overall it damped. Okay. Think of it like, if you're familiar with electric systems, right? It's RC or LC resonators. There is an L and C because of which the oscillation occurs. From, capacitor to inductor, the energy keeps oscillating. Exactly the same plot you will see. Correct? Energy entirely in capacitor, energy entirely in inductor. But if there's a resistance, that's going to dissipate some amount of energy. Overall, there's going to be a decay of energy. So now in a similar analogy, you can think of this as you have the lower state, excited state populations. Okay. If you have completely zero damping, perfect, nice. It just goes up and down forever. Okay. But that cannot happen. There is going to be some, let's say if you go to a higher state, right? All of them will not come down to the ground state. What will happen? Some of them can be randomly emitted without any proper phase, so that will cause dephasing and then it will just basically reduce the overall limit. Okay. The question was, where is energy going if the excited state population is changing up? Let's say C2 probability is up, down and up, right? So whenever the excited state has to come back down to ground state, essentially you're emitting a photon. And that photon is getting reabsorbed and then it's going back up. But in real life, it can never be such a scenario. There's going to be some loss of photons. If they escape from the system, then over, that's it. It's irreversibly lost. If the photon is completely lost from the system, then that loss is anyway there. If it's not lost and somehow it's able to again absorb back, and then the ground state can go back up to excited state. Okay. So what happens is if you have moderate damping, there is basically some amount of oscillations observed, right? In this case of moderate damping here, oscillations are damped. Okay. And if I go to the even more damping, let's say gamma is damping rate is equal to the Rabi frequency, then I'll see that there are no oscillations at all. There is some, the excited state will have some small probability. This is actually same thing that if you look at the theory, it will turn out to be the same thing that you will get from Einstein equations. So it will just be some probability up and probability in the excited state, some in the lower state. That's all over. Okay. Now, let's say here in this case, third state, no oscillations observed. Okay. What does it mean? Now, how can we observe oscillations now? If you're not seeing, because damping rate is very high. So essentially in this case, damping gamma equal to omega r, right? Now I have to somehow, if I want to see it, I have to increase my omega r. If I increase my omega r somehow, then I'll make my oscillations happen faster. Then before they can come irreversibly be lost from the system, I can observe something. So how will I increase my omega r? Electric field has to increase. Okay. So why this is happening, the oscillations are lost is basically, let's say this is due to weak electric field, right? Basically implies that omega r is small, right? And my time period for oscillation is long. In this scenario, I cannot observe Rabi oscillations. But suppose somehow I manage to increase my intensity such the electric field is large, and then I'll immediately see that my oscillations can occur. Okay. So it turns out that Rabi oscillations can be seen under high electric fields. All right.